Hello, everyone. We will be discussing now section 2.3, atomic structure and symbolism. This one will be more focused on kind of what the book is focusing on, as opposed to the first two sections of this module. We were maybe not focusing quite as much on what they looked at. So the learning objectives here: write and interpret symbols that depict the atomic number, mass number, and charge of an atom or ion. Define the atomic mass unit and average atomic mass, and calculate average atomic mass and isotopic abundance. So these are the ideas for this section. So you might remember in the last section, we sort of ended by talking about these experiments, and that the nucleus was very massive and the rest of it was empty. So this is an example of just how extreme that is. So if we had a nucleus the size of a blueberry, just one blueberry, there's a handful here, but just pick one of them, and we put that in basically the center of a football stadium, that football stadium would be the size of the atom. So the atom would be the size of a football stadium, and the whole stadium is empty except for that one blueberry. Now that blueberry would have an enormous mass. It would be on the order of, I believe, hundreds of tons, if not more than that. It would be much more massive than we can possibly really comprehend. So just very, very different. What's inside an atom is very, very different than our own experience of living. So that's a little bit about the structure of an atom. So atoms are very big, they're very small, but within that, they're mostly empty except for this very massive nucleus. Within the atom, we have basically three types of particles that we are showing here. So you want to know these particles. So we have the electron. You want to know what that one is. And for them, there's a few things you need to know. You need to know where it's located. So it's outside the nucleus. It has a negative charge. There's a specific charge in terms of what we call coulombs here. We don't need to know that. Maybe next semester this will become important, but for now, just say -1, and that's fine. And then I'm going to use a different color for this to indicate something else. I'm going to pick that color. You don't have to know that specific mass, but what you do want to know is this mass is a lot smaller than these masses. Okay, so that's the idea there. You don't have to know these numbers, but you do need to kind of know somewhat relative what they are. The other particles we need to know, we have the proton. It is located in the nucleus, and it has a positive charge. Turns out the charges of the proton and electron are exact opposites. So +1 for proton, -1 for electron. For the mass, again, I'm going to do this. You don't have to know what it is. You just have to know that it is a lot bigger than the mass of an electron. And by a lot, I mean thousands of times bigger, basically around 1,000 times bigger. So you don't have to know the specific numbers, just know basically electrons have almost no mass compared to these other things. The third one is the neutron. It is found in the nucleus, and it does not have a charge. It has no charge. I think there's a lot of chemistry jokes that that's the punchline. No charge for a nucleus, or for a neutron, I should say. And then it has a mass very similar to that of a proton. You don't have to worry that it's less than 1% bigger than the proton. They're basically very similar in mass, and those masses are much bigger than the mass of the electron. So these kind of light blue highlights are saying You don't have to know the exact numbers, but know kind of those relationships. And then the charge, specific masses, I don't care that you know those. Um, but the yellow stuff you definitely need to know. So know those particles, where they're located, what their charges are, and kind of relatively what their masses are. Okay, so these are the things that make up the atom, at least that chemistry people care about. And we talk about them in a variety of ways. So let's go ahead and get into that. We have something called the atomic number that is very important. This is the number of protons in the nucleus of an atom, is the atomic number. So you need to remember that that's what that word means. We use the symbol capital Z sometimes to represent that. If you see a Z, that Z is referring to the atomic number. We have another number called the mass number. The mass number is the number of protons plus the number of neutrons. So we call that the mass number. It's called the mass number because the protons and the neutrons have most of the mass. Almost all of the mass is from those two particles. The mass number. So atomic number, mass number. If you know these, you can figure out protons and neutrons. So atomic number is always the number of protons. So that's the definition of atomic number. And then mass number is protons plus neutrons. So you can subtract those to find the number of neutrons if that's something that you care about. Now, one thing I want to specify as we talk about this, when we talk about this, we're talking about this in relation to something called an isotope, which is a specific atom. And we'll see how that relates to a collection of atoms in an element later. For the charge of the atom, because you have a +1 charge for the proton, -1 for the electron, the charge is related to those kind of the relative amount of each of those that you have. So the atomic charge is equal to the number of protons minus the number of electrons. Now, for most atoms, that is going to be 0 because for most atoms, for a neutral atom, you have the same number of each. But sometimes they are not equal. When they are not equal, we call that an ion. Okay, so an ion has different numbers of protons and neutrons. There's two ways for this to happen. You can have more protons or you can have more electrons. So if it has more electrons, we call that an anion. So anions have more electrons. If it has more protons, we call that a cation. So cations have more protons. Now, one thing I want to stop and remember here, the atomic number is always the number of protons. So if you have more protons than electrons, it's because the electrons have gone away, not because you've added protons. So just kind of keep that in mind. There's an example here, I believe you can read through and see in your textbook, and there's some additional examples on the worksheets for this kind of a question. So in terms of the information that we get there, we can talk about the symbol of an element. So we've already kind of hinted at this a little bit in Module 1, but there's additional information to be aware of here. Here we're showing some common elements and their symbols. One thing I should mention, we briefly looked at the periodic table in the last section. All of these are on the periodic table. So if it's on the periodic table, then it is an element. And I'm not going to have you memorize these. To me, that seems like a waste of your time because the whole point of the periodic table was to avoid memorizing this information. So it's there to look at and use. So you will always be able to look at a periodic table. So don't worry about trying to memorize it. But we're just showing some examples here of elements and the symbols that we use for those elements. In many cases, the elements, the symbols are have kind of the same letters as the elements. Some of the exceptions are the elements we've known for longer that have symbols from other languages like Latin in many cases. The symbols will have either one or two letters, and it's very important that you write these correctly. So correctly means if they have two letters, the first one is capital, the second one is lowercase. So for bromine, for example, capital B, lowercase r. For cobalt, capital C, lowercase o. And this is a good one to look at because if you do this one wrong, you're talking about something else. If you have capital C, capital O, that could be capital C carbon, capital O oxygen. So it's always important that you write the symbols correctly by having capital letters, and then if there's more than one, capital, and then lowercase for the second one. If you do that incorrect, if you don't do that, that would be incorrect. And I believe your book even does talk about that, CO versus C lowercase o example there. So make sure you're able to do that. And we can find all of these on the periodic table, which we'll be looking at in a bit more detail later. So in terms of representing these chemical symbols, so part of it is the symbol of the element. So that's part of it. The other part of it is information about which particular particle you're looking at. So when we do this, we're talking about isotopes. Isotopes are they are the same element, but they might not be exactly the same. And what can be different about elements? We've already talked about ions, where you could have different numbers of electrons. You could also have different numbers of neutrons. Now, the number of protons has to be the same because that is defined by the atomic number, but the other two can change. So we can show a specific isotope or ion in a few ways. We write the symbol of the element, and then as a kind of pre-superscript, we have the mass number, and as a subscript, we have the atomic number. And then if we have a charge, we write that as a superscript after the symbol. So charges after, mass number, atomic number are before. Now the atomic number is sometimes omitted, and the reason we can do that is because, again, the atomic number is defined by the number of protons. That is the definition of the element. Each element is basically defined by the number of protons. Anything with 2 protons is going to be helium. Anything with 12 protons is going to be magnesium. So we sometimes leave this out because we can look at the periodic table and get that same information. And then for the other numbers, so these are not on the periodic table. There is a number on the periodic table that is not the mass number. It's often similar to, but it's different. The mass number is specifically this atom we're looking at, this isotope of the atom. This is saying how many protons and neutrons it has, which will be similar to what another number we'll talk about later on the periodic table. And then the charge, if you have a charge, it's because you have gained or lost electrons. You have not gained or lost protons because the atomic number is defining that. So in this case, we have 2 protons. A +2 charge is saying we've lost 2 electrons. Same thing here, 12 protons +2 means we lost 2 electrons. Here we're showing some specific elements. You don't have to memorize all of the possible isotopes here. but it's just giving you some examples of that. So what you would want to be able to calculate from this information is if you have a particular isotope, can you find, how many protons, how many neutrons, how many electrons, given this kind of information in terms of mass number, atomic number, charge. And then, of course, a periodic table if you're not given the atomic number, a periodic table to look that up for the element you're looking at. Here we're showing some isotopes of some of the smaller elements, and you'll notice we can see here's a good place to check if you know how to do this. So maybe cover up, these three columns, and then look at the symbol and see if from that symbol you could count atomic number, number of protons, number of neutrons. This doesn't have an ion example on this table, but you can, get that idea. And there are some examples of that on the on the worksheets. And you also have on this table something, the mass of a given isotope. Okay, so you'll notice that you're maybe adding together protons and neutrons in some cases. Don't worry about exactly how we get to these numbers. If you need these numbers, they'll be provided for you. But you're also given the percent natural abundance. So how much of these do you have in a sample of hydrogen? It's mostly this one and a little bit of this one. And then we see other elements, and we see other proportions. And so you have different isotopes, and you have different compositions of different isotopes. And in a naturally occurring sample of a given element on the Earth, you will have these percent abundances, and then overall you'll have a mass so an example like lithium, where you have two isotopes, you'll have something that's between this one and this one, somewhere in between. And we can calculate exactly what that is, and this is how we do that. So the atomic mass is, for a single atom, but we can find the average atomic mass. So how we find the average mass is we add up all of those possibilities. So this is a complicated, this formula might seem a little bit complicated. So let's talk about what it means. So we take the fractional abundance multiplied by the isotopic mass. And then we do that for however many isotopes we have. So that's what this I thing means. So for a given isotope, you take abundance times mass, and then you add to that whatever other isotopes you have. So if you have two isotopes, you do this twice. So this is basically saying, this is the Greek letter sigma, and it's used to represent adding together a bunch of things. So you add together those things as many times as that happens. So they're showing boron here as an example. So where do these numbers come from? If you look on the table up here, we see that boron has two isotopes, and these are their masses and their percent abundances. So we take percent abundance times mass of one isotope, and then we take percent abundance times mass of the other isotope. So we get these numbers, we add those together. That is the average mass of boron. And what that means is in any sample of boron, you're going to have about 20% one isotope, about 80% the other isotope. And then you can find out, well, what is the average overall? And this is how you would go about doing that. When you do this, it should always be a number somewhere between this number and this number. So whatever the lowest one is and whatever the highest one is, it's going to be somewhere in between there. And usually, we can see 80% of it is this one, so this number is closer to that number. So we can do this kind of calculation with that information, and there's some examples of that on the worksheets that you can work on. Another example is shown here, so you can find those. So when we do that, we end up with what we call the atomic weighted average mass, and we abbreviate that as the atomic weight. And that's something, as we look at the periodic table, we'll see where we can find that kind of information.